Hi everyone, I'm Mami Ratsim-Bazafi, and today I will talk about the design of a high-performance multithreading framework. So the multithreading framework is implemented in Nim, but everything I'm talking about is something that you can also do in C, Rust, Ada, any kind of language. And my hope is that after that talk, you will be able to implement your own multithreading framework in a weekend. So let's see how we can do that. So a bit of things about myself. I've been using Nim for 3 years now, and I'm a blockchain developer during the day, and a high-performance computing developer, and also data scientist during the night. You have my Twitter and my GitHub accounts. So, how did I start doing a multithreading framework from scratch? 3 years ago, I discovered Nim. I wanted to do some high-performance computing in Nim, and I had two threading models I could use. One is OpenMP, because Nim compiles to C, and you can add OpenMP annotation to Nim. So that makes it very easy to do parallel for loops. The second threading model is a simple thread pool, with just spawn and a sync statement. And so I used OpenMP for starter on my multithreading run, on my high-performance computing and tensor library. But a year ago, I was dissatisfied with lots of the internal, including the threading. So I started to re-implement everything from scratch. And the goal today is, as I said, end up with a multithreading runtime that you can implement in a weekend. And to go there, we need to first understand the design space. Second, understand what are hardware and software multithreading. So definitions, use cases, parallel API, and the sources of overhead, how to benchmark them, and the design constraint that those bring. So first thing, understanding the design space. One thing that you hear often is that concurrency is not parallelism. So here you have a coffee machine, or here two coffee machines. Concurrency, it's the ability of the hardware, no, sorry, of the OS or the scheduler to switch between, to interleave two threads of execution on one single resources. In case of a parallel runtime, you have two threads of execution and two resources. Another thing that you will see a lot is probably one threading, N1 threading, Mn threading. So this is about, on the left, the number of application threads, and on the right of hardware threads. And so this is something that is often seen at the OS level. So when you talk about a very old OS, they had sometimes N1 threading or 1.1 threading. But this is something that also happens at the language or the runtime level. It's just a definition, and we won't see it again. So the problem is, for multithreading runtime, how to schedule n tasks on n hardware threads. And another thing on the design space is latency versus throughput. So latency is for a single task, if you have like n tasks, and you have a single task, maybe you want the single task to be fair, like first in, first out. So this is what happens when you have multiple clients, a single server, and you are supposed to serve all your clients, let's say a web page, and you don't want to clients to spend an hour waiting until everyone else is done. Or for video decoding, if you have multiple frames and you need each frame to be processed one after the other, you need some fairness. So this is optimizing for latency. The other thing is optimizing for throughput. For example, in scientific simulations, you don't care about the single computation. You want everything, the whole work package, to be done as fast as possible. So even if the first task waits for 1 week, as long as everything is done as fast as possible, that's fine. Another design axis is cooperative versus preemptive. Cooperative multithreading, you probably heard about coroutines, fibers, green threads, first-class continuations in Scheme, for example. The characteristic is that those are lightweight, and you cannot use hardware threads for those. Second, preemptive multithreading, also p-threads, used in OpenMP, TBB, or Silk if you dive into multithreading runtimes. Those are scheduled by the OS. They have easier context switches, and you need synchronization primitives because those are real threads, let's say. So synchronization primitives can be locks, atomics, and also things that are more less known, like transactional memory or message passing. And you have I/O tasks and CPU tasks. So I/O tasks, like you're waiting for network connections or files, and you create tasks. So those are usually latency optimized and implemented via async await, while CPU tasks, they are throughput optimized, and the terms that are used usually are spawn and sync. So there is a parallel, let's say, between both API. It's just that the internals are completely different, and the requirements are different. The skills for maintenance are different. The OS API are completely different as well. So for the talk, I will focus on CPU tasks, optimized for throughput, on preemptive scheduling, so on multiple hardware threads. So now we have a bit of definitions, and let's see the different forms of multithreading that exists. At a hardware level, we have 4 kinds. There are many more, but the 4 main kinds are ILP, instruction level parallelism. So a hardware, let's say a CPU, ARM or x86, has multiple execution ports. For example, to do an addition, you have 2 or 3 ports available. They are called 0, 5, 6, something like this. And you can schedule multiple additions in parallel. That's done by the processor, as long as one execution port is free. SIMD, single instruction, multiple data. So if you heard about SSE, AVX, or on ARM, Neon, for example, those are also called vector instructions. You have an addition, and it works on 4 floating points at the same time. SIMD, single instruction, multiple thread. So those are GPUs, basically. And on GPU, you have 32 thread for NVIDIA GPU. Those are called a warp, and they have to do the exact same instructions. And for example, if you do a if branch on a GPU, it will execute both branches. And the last one, simultaneous multithreading, also called in Intel speak hyperthreading. It's a way to use all the execution ports by having logical threads sharing the same execution resources, same memory bandwidth. Because it's usually quite hard to use all execution ports at the same time. And it's not always 2 sibling cores that are used in hyperthreading. If you use Xeon Phi, it's 4 sibling cores that you have. Now, let's talk about the form of parallelism that you might want to implement or support in your runtime. First one, data parallelism. Easy, it's just a parallel for loop. If you use the OpenMP, or if you used on C++ Intel TBB parallel 4, or on Rust Rayon, that's exactly that. It's the same instruction, multiple data. Use cases, scientific computing, you have vectors, matrices, you do a for loop on all data. Challenges, how to support nested parallelism. For example, OpenMP doesn't really support nested parallelism. And there are other load balancing challenge. So it might seem surprising, but splitting a loop is, for multithreading, is actually complex. Because if you split before entering the loop, maybe you might try to split a loop in 10, even though the loop is super small and you don't need to split it. If you split, well, I won't enter into the detail because, but you have 3 splitting strategies that you can research if you want to implement data parallelism. The main one, task parallelism. So this is spawn and sync. It's basically a function call that may or may not be executed on another hardware threads, and the may or may not is managed by the scheduling runtime. An example, Intel TBB or OpenMP tasks since OpenMP version 3.0. Use cases, anywhere you want a parallel function. For example, parallel tree algorithm like depth first or breadth first search, divide and conquer algorithm. And there are multiple challenges. The API, now most of the runtimes are using futures. In Weave and in Nim, I'm using flowvar to distinguish from I/O tasks that are using futures and CPU tasks that are using flowvar. It's just a name. Other challenge, synchronization, scheduling overhead, and memory management, because you need to save tasks. Okay, 5 minutes left. Let's go fast. We have another kind of thing, data flow parallelism. 4 names, pipeline, graph, stream, data-driven parallelism. The main thing is you can express dependencies between tasks, like dependency in, dependency out, and in-out clauses. Parallel API. You have async, launch a thread that may be parallelized, await for a result. So this is for I/O tasks, and we can use spawn sync for multi-threaded tasks. Data parallelism, I talked about for loops. Data flow parallelism, there is no established API, but you can use either a declarative one, where you create a flow graph explicitly before entering a parallel section, or you can pass a handle, like a promise, to set a task ready or not. Sources of overhead and implementation details. You have scheduling overhead, because switching between tasks is costly, and switching between kernel when you need to create threads or destroy them is costly as well. Easy solution, use a thread pool. Memory overhead. You might, if you use the Fibonacci tasks, Fibonacci 40, for example, we create 2 at the power of 40 tasks, meaning trillions of tasks, and you need to deal with memory management when there is nothing to do. So you will need some clever memory management with memory pools to deal with that. And also on memory pools, sometimes you have one thread that produces all the tasks and another thread that consumes everything, and you cannot use caching in that case. So you need to handle that as well. I'm skipping on the Cactus stack and segmented stacks, but it's a complex research, and Go and Rust tried and failed and abandoned Cactus stacks. And the new GCC from 3 months ago also is stackless to avoid Cactus stack issues. Load balancing, the meat of the talk, let's say. The issue with simple thread pool is that usually you have one global task queue. You dispatch a task to a ready thread, but you have a contention issue because this task queue is, if you have 10 threads that are asking, give me a task, give me a task, give me a task, the task queue will be very busy. And the best way to scale a parallel program is to share nothing. This is Amdahl's law, and it tells you that if you have 95% of your program that is parallel, the maximum speedup that you can get is only 20. So you need to avoid serial parts as much as possible. And serial sources of serializations are the single task queue. If you have a memory pool that is also global, and you need to distribute everything on multiple threads. So one way to do that is to have work stealing. You have multiple workers, one IP. Everyone has his own task queue. It push and pop from one end of the queue, and when you run out of tasks, it gets from another worker a task. This way, the synchronization happens only if the queue is empty. This is a summary of the things related to work stealing, and there is mathematical proof of optimality, asymptotical optimality, which is why almost everyone except Julia is using work stealing. Julia is using something called parallel depth first scheduling. It's also proven optimal, but it has a different performance profile and overhead profile. It's still in development because it was released in September, and it's you can look into it. One thing that you should look into are memory models. I've given the talk from Erbsutter inside. It will, if you want to use atomics, relaxed atomics, acquire release, it's very important to watch it because it's written nowhere. I'm skipping on load balancing. You have multiple strategy to share tasks, still one, still half, adaptative, but I don't have the time to go inside. So the end, work stealing in a runtime, in a weekend, you need a task data structure with a function pointer and a blob for task inputs. Yeah, okay. Or a closure. You need a start-stop step for data parallelism if you want to express a for loop. Pref next field for intrusive queues and dequeues. A future pointer to send the result back to the caller. A work stealing dequeue with head tail field and push first, pop first, and steal last operations. And for the API, init to create your thread pool, exit to shut it down, and spawn sync to create tasks and retrieve their result. Some references, those are also on the FOSDEM website. And that's it. So
I think for one question or two, and the next speaker should come up as soon as possible.
yes. Sorry? Yes. So currently my runtime is actually at least as fast or fastest than any other runtimes. OpenMP, TBB, Rayon, HPX, Julia. So really, if you have a challenge on benchmark speed, I'm ready to take it.